In this episode, we are moving from the physical motherboard itself into the part of the system that decides how the computer wakes up, what hardware it recognizes first, what security checks happen before the operating system loads, and whether certain advanced features are available at all. New learners often hear terms like firmware, boot order, virtualization, and security settings and assume those are only for advanced technicians. But in real support work, these are basic tools for preparing a machine, diagnosing why it will not start correctly, and making sure it is ready for modern software requirements. The processor and the firmware settings work together far more than many beginners realize, because the processor provides capability and performance, while the firmware decides how the machine uses that capability during startup and early system control. Once you understand the job of the central processing unit, CPU, the role of the basic input-output system, BIOS, and unified extensible firmware interface, UEFI, and the reasons technicians adjust boot, security, and virtualization settings, a lot of startup problems stop looking mysterious and start looking like organized, solvable conditions. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at Cyber-authored in the Bare Metal Study Guide series. A processor is often described as the brain of the computer, and while that comparison is a little simplified, it is still useful because the processor is the component that executes instructions, handles calculations, and supports the operating system and applications at a very basic level. A technician does not need to become a chip designer to work effectively with processors, but they do need to understand that processors differ in speed, core count, power use, heat output, and platform support, and those differences influence what the rest of the system can do. A modern office system, a school laptop, and a workstation may all contain a processor, but their needs are not identical, which is why technicians pay attention to whether a particular machine has enough processing capability for its intended job and whether the supporting hardware is built to use that processor correctly. When a system feels slow, fails during startup, overheats, or does not support certain security or virtualization features, the processor is not always the cause, but it is almost always part of the picture, which is why technicians think about it as a platform decision and not just a speed number. Processor support is also about compatibility, which is one reason beginners can get into trouble when they assume that a new processor automatically means an easy upgrade. The board must physically support the processor, the platform must recognize the processor generation, and the firmware must know how to initialize it correctly. So technicians think about the processor as part of a larger hardware relationship rather than an isolated component. Even when the chip fits the socket, the system may still need a newer firmware version before it can start properly. And that leads to a very common support mistake where a person installs a new processor, gets no normal startup behavior, and decides the new part is bad when the real issue is that the board does not yet understand it. This is why technicians look beyond the sales label and ask whether the system board, cooling solution, power delivery, and firmware state all support the processor being used, because a correct processor in the wrong platform can produce symptoms that feel dramatic but are really the result of a compatibility gap. Firmware is the layer that sits below the operating system and gives the machine its early instructions about hardware initialization, startup order, device checks, and baseline control. Older systems commonly used BIOS in a more traditional way, while most current platforms rely on UEFI, which offers a more modern framework for startup behavior, hardware support, security integration, and storage handling. For a new learner, the easiest way to think about firmware is as the system's early decision maker, because before the operating system can take over, firmware determines whether the processor is recognized, whether memory is initialized, whether storage devices are visible, and which device the system tries to start from first. That makes firmware settings extremely important in support work, since a computer that refuses to boot from the correct drive, ignores an installation device, behaves strangely after a hardware change, or fails a security requirement may not need a hardware replacement at all and may instead need a careful review of its firmware configuration. One of the most practical firmware ideas for a beginner to master is boot order, because it affects what device the computer checks first when starting up. If the machine is told to look at the wrong drive, a removable device, or a location that is not prepared to start the system, the user may see error messages, blank startup loops, or confusing behavior that feels larger than it really is. Technicians use boot order settings when they are preparing a new installation, recovering from a startup problem, or making sure a system returns to its main storage device after maintenance is complete, and they treat this as routine platform setup rather than a rare advanced task. Many support calls are solved simply by realizing that the machine is trying to start from the wrong place. And that is an important lesson because it shows how a system can look broken even when the processor, memory, and storage are actually fine, and only the startup path is misdirected. Startup issues also appear when firmware settings have been changed without a clear reason, especially after hardware work, system resets, or poorly understood attempts to improve performance. A system may fail to detect a drive, may pause during startup, may ignore a new installation device, or may behave as though the operating system is missing. And while beginners often jump straight to hardware failure, technicians know that incorrect firmware settings can easily create the same symptoms. This is why they check whether storage mode changes, disabled devices, reset defaults, or unusual startup priorities are influencing the machine before replacing working parts. In support practice, the calm and reliable approach is to treat firmware as one of the first places to verify when a machine powers on but does not proceed normally. Because the computer may be telling you that it still has electrical life and basic hardware function even if its startup instructions are currently wrong. Security settings in firmware are another area that matters more now than many older repair habits would suggest. Computers are no longer judged only by whether they turn on and load an operating system, because modern environments also care about whether startup can be trusted, whether unauthorized changes are harder to make, and whether security technologies required by the operating system are available and enabled. Technicians may work with firmware passwords, device control settings, and platform security options that help reduce the chance of tampering or unapproved changes before the main system software ever begins. The key beginner lesson is that firmware security is not there to make life difficult for users or support staff, but to establish trust at the earliest stage of startup, since a machine that begins from an untrusted state can undermine every protection that comes later, even if the operating system itself seems normal once it loads. A major example of this startup trust idea is Secure Boot, which is designed to help the system verify that the software involved in the startup process has not been replaced by something untrusted or malicious. You do not need to know every internal detail to understand why technicians care about it, because the practical effect is that it can help block certain forms of low-level tampering and can also affect whether some operating systems or recovery tools will load as expected. This means support work sometimes includes checking whether Secure Boot is enabled, whether it needs to remain enabled for policy or operating system requirements, and whether a startup or installation problem is happening because the machine is refusing to trust what it sees. A beginner should understand that this is not just a box to turn on and forget, since a technician must balance functionality and security while avoiding the careless habit of disabling protections simply because they seem inconvenient during a single troubleshooting session. Another important platform security feature is the Trusted Platform Module, TPM, which is a hardware-based component or function used to support certain trust and protection features in modern systems. Many new learners first encounter TPM only when an operating system or security tool says it is required, but the deeper point is that it helps the system store and support security information in a more protected way than ordinary software alone. A technician may need to verify that TPM is present, enabled, and operating correctly when preparing systems for modern deployment, supporting device encryption, or meeting security expectations in business and education environments. That means TPM is not merely a checkbox for operating system installation, because it is part of a broader trust model, and when it is disabled, missing, or misunderstood, the result may be failed upgrades, broken security features, or confusion about why a perfectly powerful computer still does not meet the platform requirements placed on it. Virtualization support is another firmware area that often confuses beginners because the word sounds abstract until it is attached to a real use case. At a high level, virtualization allows one physical computer to support systems or environments that behave as though they are separate machines, and that can be useful for testing, training, software compatibility, development, and certain business workloads. The processor plays a major role here because modern processors include features that help virtualization work more efficiently and more safely. And those features often need to be enabled in firmware before virtualization software can use them. When a user or technician is told that a program cannot start a virtual machine, VM, or that hardware virtualization is unavailable, the processor may already support the function perfectly well, but the firmware may still have the relevant setting turned off. Which is why support technicians learn to connect software complaints back to platform settings instead of assuming every problem begins and ends inside the operating system. This is also a good place to clear up a few common misconceptions that cause wasted effort. A faster processor does not automatically solve poor system behavior if the real problem is heat, storage delay, bad memory, or wrong firmware settings. And enabling every available firmware option does not make a machine better simply because more features sound impressive. In the same way, disabling security settings to get around a short-term inconvenience may create a longer-term platform weakness, and turning on virtualization support without understanding the environment may confuse later troubleshooting if a user does not even realize those features are active. Good technicians are not the people who change the most settings, but the people who understand why a setting exists, what symptom or requirement justifies changing it, and what side effects should be expected once that change is made. Because firmware settings are powerful, technicians approach them carefully and methodically rather than guessing their way through menus. They document what they change, pay attention to the current startup device, verify whether security requirements must remain enabled, and avoid the dangerous beginner habit of changing several settings at once and then forgetting which change affected the system. They also understand that some startup problems appear after updates, resets, or hardware replacements because the machine has returned to defaults or because a once working combination of settings no longer matches the new hardware. That is why the disciplined workflow matters so much, since stable support does not come from magical instincts, but from checking compatibility, reviewing the current configuration, changing only what is necessary, and confirming that the machine still meets the functional and security expectations of the person or organization using it. A simple support scenario helps tie these ideas together. Imagine a desktop that powers on, shows the vendor screen, and then fails to load the operating system after a storage replacement, while another machine seems healthy but cannot run virtualization software needed for training, and a third one is being prepared for a modern operating system that expects stronger platform security. In the first case, the technician may review boot order and storage recognition before touching hardware again, because the drive may be present but not selected correctly. In the second case, the processor may already support virtualization, but the relevant firmware option may be disabled, while in the third case, the machine may need secure boot and TPM enabled before deployment can proceed, which shows that startup, security, and virtualization are not separate little topics, but connected parts of how a modern platform is prepared and supported. Another useful mindset for a beginner is to stop viewing firmware menus as mysterious screens that only experts should open in emergencies. A technician respects those settings, but they do not fear them because they know the menus exist to control startup behavior, hardware readiness, and trust features that matter in normal support work. The processor, firmware, boot settings, security settings, and virtualization options all sit near the boundary between the physical system and the operating system, which is exactly why so many frustrating problems begin there and why so many clean fixes are found there too. Once you understand that relationship, a machine that will not start correctly, a platform that fails a deployment requirement, or a system that cannot run expected software becomes less of a mystery and more of a puzzle whose main pieces are already visible if you know where to look. By the end of this topic, the processor should feel like more than a speed component, and firmware should feel like more than a screen you tap through during startup. The processor determines major capability, while BIOS and UEFI settings shape how that capability is recognized, protected, and used when the system begins operating, which is why technicians care about boot order, security features, and virtualization support even in ordinary support situations. A computer that fails to start, fails to meet a security requirement, or fails to support a needed feature is not always suffering from broken hardware. And often the real answer is that the platform is configured incorrectly for the job being asked of it. When technicians understand those connections, they do not just fix startup issues more efficiently, they also prepare systems more intelligently, avoid unnecessary part replacements, and support modern computing needs with much more confidence from the very first power on.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.